I'm Dr. Andrew Franklin, Assistant Professor in the Department of Psychology at Norfolk State University, and this is a video in which you can find a standard deviation tutorial. For the purposes of this video, I will utilize the definitional formula because it goes hand in hand with the actual definition of a standard deviation. Standard deviation is the average distance that an abundance of raw scores are from the mean. Let me go ahead and write out the definitional formula for the standard deviation. So we have a lowercase s, which basically means sample standard deviation within statistics. And I really want to emphasize the sample piece because that will serve as a key distinguishing bit of information when we talk about the population standard deviation. Let's get back to our formula. We have a sigma here, which means sum, and we have x minus the sample mean, which is denoted here as a capital M, and then we have that over n minus 1. N minus 1 is the degrees of freedom. So this is the amount of variation you should expect to see within a sample. And one number is set aside to be a specific number because keep in mind that all of your numerics within a sample must balance out around the mean. I'm going to put a square root over everything, and I want to be careful to add that exponent there, as that's a critical piece en route to calculating our sample standard deviation. So since I've already pointed out that the S stands for sample standard deviation, you know that n minus 1 is degrees of freedom, or you may see an abbreviation of DF. Let me go ahead and point out the rest of these abbreviations or symbols. This, of course, means raw scores. This is your sample mean. And even though I already explained it, we'll just write out that this means sum. So, just for clarity's sake, I'm going to apply the order of operations to this statistical formula that you see. And in doing so, I will break down step by step what you need to do in order to calculate a sample standard deviation. One is you need to calculate sample mean. So if it's not already given to you, you need to calculate that based on your data set. Second thing that you need to do is calculate deviation scores. A deviation score is the distance that a raw score is from the mean. So that would be this part of the formula. So that's everything in parentheses. After you do that, you will square your deviation scores. That would mean doing all of this. And the reason why we're squaring deviation scores is because if we were to take our true mean and subtract it from every raw score, and then go the route of summing up all of those deviation scores, we would end up with a 0 because all of the numbers balance out around the mean. So we overcome this impasse by squaring our deviation scores so that we can eventually get to the point of calculating the average distance that all the raw scores are away from the mean. So after you square your deviation scores, you will sum your square deviation scores. This is oftentimes referred to as the sum of squares. After you calculate the sum of squares, or you do everything in your numerator here, the next thing to do, according to the order of operations, is divide that sum of squares by n minus 1. Divide sum of squares n minus 1 to get the variance. A variance is the average square distance that all the raw scores are from the mean. So oftentimes the variance isn't something that's held in high esteem within statistics. So essentially it just serves as a precursor to calculating our sample standard deviation. Our final step is to take the square root of the variance. This will ultimately give us our standard deviation. So when we take the square root of the variance, we are undoing what we did here. And the reason why we did what we did at step 3 was to overcome the difficulty that we found ourselves in step 2. Okay. So let's say we had a hypothetical data set of 8, 1, 5, 1, 5, and let's say this was a sample. Lowercase n typically means sample. So according to our steps here, what we need to do is calculate a sample mean first. Calculate our sample mean. When we sum up all of our raw scores, we end up with 20. And then when we divide 20 by 5, we end up with 4. So that's step 1. Step 2 would be calculating our deviations. So we calculate a deviation for every raw score. So we place all our raw scores below this column. And we take 4 from 8, 4 from 1, 4 from 5, 4 from 1, and 4 from 5 again. So we have taken care of step 2. Now, many people would say if we want to know the average distance that all of these numbers are from this mean, then it would make sense to just add all of these up and then divide by the sample size. After all, that's how you would go about calculating an average. However, you would run into issues if you tried to do that. If we add up 4 plus -3 plus 1 plus -3 plus 1, we will end up with 0. And if we try to take 0 and divide by 5, we're going to end up with 0. So we are not going to get meaningful information that way. How do we overcome this impasse? We overcome it by taking the square root of all of our deviation scores. So that's what we are doing in step 3 as a means of taking care of the issue we encounter in step 2. So we go 4 squared, 3 squared, 1 squared, -3 squared, 1 squared. We end up 16, 9, 1, 9, and 1. Now, moving forward, we need to sum our square deviation scores. Step 4. So we have 16 plus 9 plus 1 plus 9 plus 1. And that gives us 36. Our next step is to divide the sum of squares by n minus 1 to get the variance. So 36 divided by n minus 1 in this particular case, 36 over 5 minus 1, okay, because 5 is our sample size. Give us 4 in the denominator, 36 in the numerator, and then ultimately our average squared distance that all of these scores are from the mean would be 9. So we have effectively taken care of step 5. Finally, with step 6, we will take the square root of 9 to get a final answer of 3. So what this means is that all of these numbers, 8, 1, 5, 1, 5, are on average about 3 points away from the mean of 4. So that is how you calculate a sample standard deviation. Again, I'm using the definitional formula because I prefer it over the computational formula. Definitional formula goes hand in hand with the definition, which is why I like to use it. I do want to talk just briefly about the population standard deviation formula. Let's differentiate it from the sample standard deviation formula. So the population standard deviation formula looks very similar to the sample standard deviation formula, but there are two key pieces that are worth noting. One is that in parentheses you have a population mean, and the other key piece that's worth differentiating this formula from the sample standard deviation formula is that in uppercase N is in the denominator, and this is the population size. So if we were to say that this sample was a population, essentially what that would mean is when we got to step 5, instead of dividing by n minus 1, we would divide by the population size. In step 2, we would still be taking the mean from each raw score, but instead of the sample mean, of course, we would be utilizing mu, or the population mean, in its place. Of course, we'd have to make an adjustment here, say population mean instead of sample mean. So, key differentiating piece between population standard deviation and the sample standard deviation is the denominator mainly, and then you have a distinguishing piece found in the parentheses, where here there's an emphasis on population mean, here there's an emphasis on sample mean. I mentioned that n minus 1 is degrees of freedom and how it's used to ensure that there is one score within the data set that will ultimately cause all of the numbers to balance out around the mean. In other words, it makes sure that when you sum up all the calculation deviation scores, you get a 0. That's one role of the degree of freedom. Another role of the degree of freedom is that it's an unbiased estimate. In other words, it helps the sample to be better representative of the larger population. And this is done by increasing uh, the the numeric that one would eventually end up with when they are calculating a sample statistic by decreasing the numeric in the denominator. So for a sample, to drive that point home, my sample standard deviation is a 3, but if this was a population, you would likely find that the population standard deviation would be much smaller than 3. So the sample statistic allows us to get a better estimate of what the population may be, and that is done utilizing the degree of freedom. So that concludes this tutorial. I hope that this was helpful. If you have any questions, comments, or concerns, feel free to leave them below. And I look forward to presenting you with new content soon. Take care.